This is just a recap of today's class on algebraic fractions coming from Appendix E. So we started off saying that, hey, a fraction is just an expression in which one number is divided by another. And well, we can do this for things that aren't just numbers. We can have the components, the numerator and denominator of our fraction, being expressions. That works just as well. So an algebraic fraction is one where we have one expression divided by another. So for instance, q plus 3 divided by 2q minus 5 is an algebraic fraction. And it has a lot of the same properties as an ordinary fraction. It's just that we have to have some additional tools for how we work with it. Okay, so there's a technicality, one of the immediate things we want to think about. We can't divide by 0. You can't have a fraction where the denominator is 0. So algebraic fractions themselves are going to be undefined for values that make their denominators equal to 0. So let's try to avoid doing that. Or when we solve our problem, we get our final expression, let's just figure out what values of the variable aren't going to be possible. So in this case, if we have q plus 3 divided by 2q minus 5, let's just go ahead and find when the denominator is 0, because that'll make this whole thing undefined. Well, in order to do that, I'll just take this denominator, I'll set it equal to 0 and solve for the variable. That's just simple algebra. We find when q is equal to 5 halves, or 2.5, then the denominator is 0, and this whole expression is undefined. It's only defined for values other than q is equal to 2.5. Okay, we can show this. Let's actually evaluate the expression. Evaluating the expression means we're going to plug in a particular numerical value for the variable, wherever that variable appears in the fraction. So it's here and here. And I'll just do these operations, and I find, oh look, the denominator is 0. That's exactly as we expected. So clearly when this thing, this whole expression is undefined when q takes on a value of 2.5, or written this way, 5 halves. Okay. Well, we can cancel terms with algebraic fractions just as we can with simple common fractions. So here's an example. 4/10. We can factor out a 2 from the numerator and the denominator, because 4 is just 2 times 2, and 10 is just 2 times 5. So I've canceled, and I get 2/5. Well, just as this works, where the term appears in both numerator and denominator, if we can do this with an algebraic fraction, we can cancel as well. So our general strategy is just, let's remove the common factor from the terms in the numerator, repeat for the denominator, and cancel where possible. It doesn't matter if we have numbers or if we have letters, expressions. All we're going to be interested in doing is whatever is the common factor, let's find it, let's factor it out, and then look and see what is going to be possible to cancel from the top and bottom of our expression. Okay, so let's try some examples. Let's go back to, so we have, let's simplify this algebraic fraction by cancellation. We have 5q minus 5 over 10q. Well, clearly we can factor a 2 out of the numerator. We can factor a 5 out of the numerator, sorry. We can factor a 5 out of the denominator, and then we can cancel. And we're left with q minus 1 over 2q. Why can't we cancel that q? Well, if you don't understand at this point, just plug in some values. Q is equal to 1, q is equal to 2, and compare it to minus 1/2. Why minus 1/2? Well, if we did cancel these 2's, or these q's, what do we have? Minus 1/2. And if you plug in these values, you'll see that, clearly we're going to have something very different from minus 1/2. Okay, more rigorously, what's going on? Well, we can't cancel the q because we can never cancel across addition or subtraction. We can only cancel across division or multiplication. So another way to say this is q enters the numerator additively, and it enters the denominator multiplicatively. Okay. So we can simplify this example. We have an expression with an algebraic fraction. So we have expression in the numerator, we have an expression in the denominator. Here I'll factor out 12, because 12p and 24q can both donate a 12. And I can factor out a minus 3 from the denominator. And then just staring at this, just to make sure we're right, what happens if I distribute this 12 back? Well, I get the same numerator. What if I distribute this minus 3 back? Well, I get minus 15p, and I get minus 6q. Okay, so our factorization was correct. Can we cancel anything? Well, sure, we can cancel a 3 out of the numerator and the denominator. We're left with a 4 in the numerator. Initially, this looks a little weird because you see a 5 down here. Where'd that come from? It's not that we factored out a 5, it's just that we dropped these parentheses. So now we just have whatever was that expression. Okay. Let's try this one. We have 3a squared, or 3a cubed, plus 6a divided by 6a squared plus 12. I can factor out a 3a. I can factor out a 6. And the neat thing here, well, there's a couple neat things. One is, the part that cancels is actually the remnant after we've been factoring. It's this a squared plus 2 term. That's the expression we're actually able to cancel. We're left with 3/6 a. Clearly 3/6 is just 1/2, so we have a over 2. And here's the other cool part. In order for this cancellation to be valid, we need to be the case that this expression, a squared plus 2, is never 0. Why? Well, that appears down here in this denominator, and if this were ever 0, then at those values, that would make it 0, the entire thing would be undefined. Of course, that doesn't happen here. A squared plus 2 is always positive. We don't have to worry. It's always true. Okay. Here's another one. Let's factor the numerator and denominator to simplify. So we have x minus 3 divided by 6 minus 2x. There's a couple of different ways to do this. What I decided to do is factor out a minus 1 first, because we're going to do a lot of factorization that involves bringing out a minus 1. You could have done something different. Ultimately, hopefully, we're going to get something that looks like this. X minus 3 divided by minus 2 times x minus times the quantity x minus 3. We can cancel our quantity x minus 3, and we're left with minus 1/2. With this additional restriction, this is valid. Our expression is equal to minus 1/2 on the assumption that x is never equal to 3. Otherwise, it's undefined, because if we plug in a value of 3 into our denominator here, you'll see clearly we get a divide by 0 problem. Okay, so in the next two exercises, what we're interested in doing, or examples, what we're interested in doing is showing that whatever is on the left-hand side is equal to whatever is on the right-hand side. Well, the left-hand side is minus the quantity p minus q divided by q minus p. And our strategy is to pick either the top or the bottom and factor out a minus 1. Doesn't matter which one. You just have to factor out a minus 1 from the top or from the bottom, and then cancel where possible. Well, I have this minus 1 right here. If I'm going to be factoring out a minus 1, I might as well factor out a minus 1 from the bottom, and then my negatives will cancel. So that's what I've done. When I factor out a minus 1 from this q, that changes its sign to negative. When I factor out a minus 1 from this minus p, that changes its sign to positive. So rather than q minus p, I now have p minus q multiplied by this negative. And check what happens if we distribute this negative back. Sure enough, we get our original denominator. We can cancel our minuses, cancel our expressions, and 1 is equal to 1. So we know our original equality was a true statement. Okay, so we can try this again for another expression. On the assumption that x is not equal to y, let's show x minus y divided by y minus x is equal to minus 1. I mean, maybe by now you can stare at it and realize that this has to be true. If not, well, let's factor out a minus 1 and then cancel. So here I'll factor a negative out of the denominator. Our numerator and denominator cancel with each other. This entire expression, x minus, or the quantity x minus y, cancels with the quantity x minus y. We're left with minus 1, which tells us our original equality was true. This left-hand side indeed was equal to the right-hand side, which was minus 1. Okay, so for the next example, I'm going to invoke this principle we should remember from earlier, which is the difference of squares. So this is actually a difference of squares, a squared minus b squared, and the factorization is the quantity a minus b times the quantity a plus b. So maybe it's easier to see if I start from this, though. Think about using FOIL, or think about distributing the quantity a minus b to a and then to b. Either way, you'll get this line, a squared minus ba plus ba minus b squared, or you'll get a squared minus ab plus ab minus b squared. But addition is commutative, or multiplication is commutative, so it doesn't matter if we have ba or ab. and then you'll have a squared minus b squared. Okay, so we're going to use that in the next example. Let's simplify 3k squared minus 27 divided by 3k. If I factor out a 3, I'll get k squared minus 9. And we can recognize anytime we see this k squared minus something, I'm always going to be curious, is this a difference of squares? Well, sure enough, we can write 9 as 3 squared. And if 9 is 3 squared, then we can think of k as a, 3 is b, and then we know we have a minus b times a plus b, looking back at our difference of squares rule from here. Okay, so I have k squared minus 9 is going to be, I can also write this as the quantity k minus 3 times the quantity k plus 3. When I do this, we see, okay, we have something that almost looks like it can cancel. We have to factor out a minus 1, and then it'll cancel beautifully. And indeed, our expression simplifies down nicely just to its numerator, minus 3k plus 3. Minus 3 times the quantity k plus 3, sorry. Okay, here's another example, adding algebraic fractions. Suppose we want to write the sum I over 11 plus 4i over 11 as a single fraction. Well, of course, we know we have a common denominator, we can just add the numerators, and then we're done. Suppose we want to do this using our new tools. And the value of doing this is just to get some additional practice using the principles we've been working with. Not that it's particularly useful on an example as easy as this, but sometimes it's nice to see those tools in action on more simple problems that they're available to us on more difficult ones. So let's do that. Let's write this as a single fraction. What this amounts to needing to do is just factoring out this 1/11th. 1 over 11 times the quantity I plus 1 over 11 times the quantity 4 plus I, or 1 over 11 times the quantity I plus 4i. Here I factored out the 1 over 11, did the addition, and I've got my 5i over 11. So when you look at this, you shouldn't approach this as thinking that this is just a really long way to get to the same thing we could do here. The right way to look at this is to say, oh, look, here we've used our principle of factoring out this fraction, and then sort of a reverse distributive property. And then here we've used here we've added, collected like terms, and then we have our final result. Okay. Here's another example. Let's use the distributive law in reverse to express the fraction as a sum of fractions. So let's write 3x plus y divided by x plus 4 as the sum of two fractions. Here's a hint. It's not this. This is very wrong. 3x plus y over x plus 3x plus y over 4 is definitely not the way to write this, because when we add these two fractions together, we get something very different. Right? We'd actually get something with a denominator of 4x. Right? Think about having to get a common denominator. You'd have to multiply this thing by 4 over 4. You'd have to multiply this thing by x over x, and then add. Much different than this right here. Okay, so instead, we're just going to forget about that. That was just to illustrate. We're going to write 3x plus y divided by x plus 4 as a sum of two fractions. How can we do this? Well, let's factor out the 1 over x plus 4 term. If we do that, here is the denominator, here is the numerator. All I've done is I've written the fraction as multiplying the numerator by 1 over the denominator. That's all that was. And now I'm writing this as the reverse of the distributive property. So this 1 over x plus 4 times 3x plus 1 over x plus 4 times y. And then I'm just writing these as fractions. Okay, so look at this result right here. This is the correct way to write this thing as a sum of two fractions. And remember, this was not at all correct. See how we have very different denominators? Okay. Here's another one for practice. Let's write p over 32 plus q over 40 as a single fraction. How do we do this? Well, we have to get a common denominator. So 32 times 40, 32 times 40, and then over here, 40 times p, 32 times q. What did we really do? Well, we multiplied the left one by 40 over 40. That's legal because 40 over 40 is just 1. We multiplied the right one by 32 over 32. Again, that's just a clever way of writing 1. And then we can add the numerators. Here I've written the denominator as its product, right? 32 times 40 is 1280. And then I decided to simplify it down a little bit. I realized I could factor out an 8 from the top and the bottom, and this is the best I can do. 5p plus 4q over 160. So in general, if we're using operations on algebraic fractions, if we have addition, we can add and subtract algebraic fractions, provided that b and d are not 0. Why can't they be 0? Well, b and d are our denominator. If they're 0, then these fractions are undefined, and of course their sum is going to be undefined. So what's the rule? If you have a over b plus c over d, this turns out to be a times d plus c times b divided by bd. Doesn't matter if these are numbers, expressions, whatever. Whatever is in the a position gets multiplied by whatever is in the d position. Whatever is in the c position is multiplied by whatever is in the b position. And those two products are added to each other and divided by the product of the denominators. What's going on there? Well, that's what happens. This is literally what happens when you get a common denominator, right? So you multiply both sides by d over d. I mean, you multiply this left-hand side by d over d. You multiply the right side by b over b. You multiply both sides by 1 written cleverly. Same thing for subtraction. What's the difference between add and subtract? Just the sign. So probably it's better not to memorize these formulas so much as the value of seeing this slide. The value of seeing the next slide isn't so much memorizing the formulas, it's just recognizing the pattern. Okay, so here we can multiply and divide algebraic fractions. So a over b times c over d is equal to, well, a over c divided by b over d. What do? We just multiply numerator to numerator, denominator to denominator. And this works provided that b, c, and d are not 0. Well, actually, this is my note for division. So here, perfectly fine if c is 0. What happens then? This whole thing is 0. Really bad if b or d is 0. Then it's undefined. Okay, so if we have division, we have, let's say, a over b divided by c over d. Well, dividing by a fraction is the same as multiplying by its reciprocal. So a over b divided by c over d is going to be ad divided by bc, provided that bc and d are not 0. Why? Well, though d appears in the numerator here, it was a denominator here. And though c was a numerator here, it's a denominator here. So that's why. So the following examples have value primarily in helping us recognize and appreciating the patterns, which is what I was saying. It's possible to memorize the generic expressions and substitute accordingly, but I say that's probably not a good strategy. In the long run, you're going to forget the formulas. I forgot them, but I can still do the problems, and hopefully you'll be able to too, because I internalize the algebraic rules that the formulas came from, and so that's far more valuable. Why do we show the formulas to you? Well, not for you to memorize them, but just so you to recognize the pattern of what happens when you get a common denominator and when you follow the rules of algebra. Okay, so here's an example. Let's express 4 over q divided by 4 over q plus 5 over q plus 5 as a single fraction. So we're going to use our addition rule. You'll see this first line I just took, well, 4 is a, d is this q plus 5, so I have 4 times q plus 5 plus q times 5. That's my CB part, divided by the product of the denominators. What did I do there? You really just got a common denominator, but of course what I did is I substituted according to this formula. Okay, so then we distribute, collect like terms, and then simplify down. Why can't I cancel this q? Well, we don't have a q to cancel. We can't cancel across a plus or a minus, and this 20 doesn't have a q to donate. Okay. Here's another one. Let's express x divided by y plus x minus y divided by y minus x as a single fraction. So here we're going to use our subtraction rule. And if you stare at this and work through this example, you'll see all I did is just got a common denominator and then did the subtraction. Or you can look and see where this formula was applied. what the pattern was. Okay, to simplify this down, well, we collect like terms. This xy cancels that xy. I get a minus x squared minus y squared. I'm going to look for something to cancel. My initial thought is, well, maybe I can turn this into a difference of squares. Of course, that doesn't happen because I have a minus x squared minus y squared. So then the next thought is, well, can we do something clever down here? Wait, that's a difference of squares staring at us. So we have y squared minus x squared. And then we can make this look a little prettier by factoring out a minus from the numerator. And then we'll have a minus x squared plus y squared divided by x squared minus y squared. Well, the minus is for the whole fraction, of course. It's not exactly how I said it. Negative the fraction x squared plus y squared divided by x squared minus y squared. Okay, here's another one. Here's a multiplication one. 4 divided by quantity p plus q times pq squared divided by 5. Just multiply numerator to numerator, denominator to denominator, and here's our result. Nothing cancels. Can't cancel this q with that q because we have a plus sign. Can't cancel this p with this p because you have a plus sign. This is the best we can do. Okay, here's the division one. We can divide 4. Well, the fraction is 4 divided by the quantity p plus q in the numerator, and the denominator is pq squared divided by 5. Well, dividing by a fraction is the same as multiplying by its reciprocal, so let's do that. And then this simplifies down to 20 pq squared times the quantity p plus q. Okay, so now a couple exercises. These are ones that we had. This is the ones that we had on the board. So here's the solutions. We have x squared minus x minus 12 divided by x squared plus 2x minus 3 times x minus 1 divided by 12 minus 3x. So I'm going to factor the numerator. Then I get x minus 4 times, or quantity x minus 4 times the quantity x plus 3 divided by the quantity x minus 1 times the quantity x plus 2, or x plus 3, sorry, multiplied by quantity x minus 1 divided by 3 times the quantity 4 minus x. What did I do? Well, this factorization is pretty easy. Just look and see what happens if we FOIL this. Of course, we get this as a result. This bottom one, maybe that was a little trickier because this has this coefficient is 2. That's not too bad, though. And then over here, I just factored out a 3. I can cancel some stuff immediately. This quantity x minus 1 cancels. This quantity x plus 3 cancels. What about this 4 minus x? Well, it's the wrong sign, so I need to factor out a minus 1. That allows me to switch the order the variable appears in the sum, and then I can cancel. Sure enough, this simplifies down really nicely to minus 1/3. And this whole messy thing turns down to this relatively harmless-looking fraction. Okay. So we can simplify this one. Here we have division in the numerator, division in the denominator. So I'll just write this first one as our initial fraction. The other one I'll write actually with this as the numerator, this is the denominator, right? Because we have dividing by a fraction is multiplying by its reciprocal. And that just canceled everything immediately. And we have p plus 4 over p. Well, I factored and then I canceled everything immediately. Anyway. Okay, so here we have q squared plus q minus 6 divided by q squared minus 1 times q minus 1 divided by q minus 2. So just factor the numerator, factor the denominator, and then do this multiplication. Well, we can cancel a whole bunch of things right from the get-go. So this quantity q minus 1 cancels with this one. This quantity q minus 2 cancels with that one. And we're left with this, actually just these first terms. Q plus 3, quantity q plus 3 divided by the quantity q plus 1. And then I say, well, this works as long as q is not equal to minus 1, 1, or 2. Why? Well, those are all the values of the q that would make the denominator 0 in our original product. So those are the restrictions on q. Okay. Here's another one. Let's write as a single fraction, 1 over q minus 3 minus 1 over q minus 2. Here we're going to use our expression, the subtraction 1, our formula, subtraction 1, or just get a common denominator. If you're doing that, you're going to multiply both of the left fraction with the quantity q over 2 divided by the quantity q over 2. And you're going to multiply both of the quantity, the right fraction with the quantity q minus 3 divided by quantity q minus 3. Why? That's just 1 written cleverly. If we do that and then subtract, this is our result. Or if you look to the formula, here's where we end up with. Well, from this point I actually can't cancel anything just yet because this minus in the numerator, though it's tempting because I have a q minus 3 and a q minus 3 and a q minus 2 and a q minus 2, this minus sign keeps me from being able to cancel. But what I can do is I'll just distribute through this 1. That amounts to just removing the parentheses. I can distribute this minus 1, so I remove the parentheses and then I can change the signs. And then I'll just do the addition. I'll collect like terms. Well, q's go away, minus 2 and 3 is 1. And actually this is going to be our result. Okay, so here's one more. This one doesn't look so nice. So we have 1 plus the fraction 1 over 1 plus 1 over x. Okay, well, if you apply the formula, that's probably the easier way to approach this. So we go back to our addition formula. Right, so we're going to use this thing right here. And actually, if we do that, this thing simplifies down pretty quickly. Now, if you stare at this long enough, you realize, again, all we did is get a common denominator, and then we did the addition. And if you do that, well, you actually get not such a bad result. 2 plus 1 over x divided by 1 plus 1 over x. And then we can actually do a little bit better from that point. What do we do? Well, let's get a common denominator from the numerator. Let's get a common denominator from the denominator. And if we do this, well, if you're staring at this, there's two ways we can do this. Right? One thing we could do is we could just say, oh, we have an x here, we have an x there, let's cancel those, and then this 2x plus 1 collapses down on top of this x plus 1. Right? Or you could take this fraction and realize that dividing by this fraction is the same as multiplying by its reciprocal. We have an x here, we have a x plus 1 here, and then those x's cancel. We move over. I don't know. However you want to think about our simplification, either way we end up with this 2x plus 1 divided by x plus 1, which is way nicer than this original statement. So, pretty neat. All right, so here we have 1 over a plus 1 over b. Let's get a common denominator in the denominator. And then I'm going to write this as, this is a division. I'm going to write this as fraction division. So I'm going to write this as a fraction that I'm sort of inventing, 1 over 1, divided by b plus a over ab. That allows me to write this as 1 over 1 times ab over b plus a. And then this is just a much nicer thing to look at than this. Okay, and then the last one. Suppose we have something like this, 1 over m minus 1 plus 2 over m plus 2 divided by, just by itself, 3 over m plus 2. So I'll get a common denominator in the numerator. So that's this right here. Or you could apply that addition formula that I showed a second ago. I like the common denominator approach. I realize I'm missing some parentheses here, aren't I? Sorry about that. There should be parentheses around this quantity m plus 2. This actually looks like, this is terrible, this actually looks like it's m plus 2, which will be distributed by this. I don't want to fix the video. I'm already at the end. I like the last slide, so I'm just going to leave this. So just for your notes, and as you're watching this now, just right here, put parentheses around this m plus 2. That shouldn't be too surprising because we're getting a common denominator, and I actually did it correct down here, right? Okay. So now I've got a fraction divided by a fraction, and I can rewrite this as a fraction times the reciprocal of the second fraction. So that's what I've done here. I get a common, or I add like terms in the numerator, and then multiply by this portion. Boy, there's another typo there. Sorry about that. Just take out this parentheses. Doesn't matter because this gets canceled off, and then we have what? We just have m over m minus 1. I should have canceled this 3 here too. I'll fix that on the upload. But if you're following through, I'll just leave the slide for a second on the video so you can figure out what it should have been. Okay, and we've reached the end. So let me know if you have questions.